Okay. So we know nowhere else nearby. So how can we use this? So we want to somehow get a contradiction. And we want to contradict the fact that it's not one-to-one. So the problem is we don't want there to be such a point Z2. The presence of the point Z2 is causing trouble. So we want to show that there can't be. So we want to somehow study what's going on near Z2. So the question is, what is a good thing to study related to our functions f and g and fn? And what do we know about the function gn near z2?
Near z2?
Yeah. What's going on?
Really small, right?
We don't know.
Oh, that's
Probably because gn of z2 is converging to 0. So it probably is small near z2.
Right, but it might be.
But we should know something about its value.
We need it non-zero.
It's non-zero. So gn is going to be non-zero near z2. So what am I allowed to look at? 1 over. So can you think of anything involving 1 over gn that's worth looking at?
Looking at
gn prime. Yeah.
Okay,
yes.
gn prime over, you can either split the M&M, you can each have an M&M.
I already had it.
So what should we look at?
G prime n, or G prime n over gn. Yeah, that's good.
So in complex analysis, this is one of the key things to look at. We'll look at a small circle about the point z2. Gn prime of zeta over gn of zeta d zeta 1 over 2 pi I. What does this count?
The number of zeros minus.
And what is this equal to? How many zeros and how many poles does gn have inside a small circle of radius about z2?
1 0. 2. Oh no, the limit does. Okay.
The limit has a 0.
1 0.
How many zeros does gn have?
1 0.
0.
It's only going to 0.
The only 0 of gn.
Oh, okay.
Alright, now this is why I want to be very careful. This is why we're using red. This is a very expensive lecture. I have to use. We don't know, if we don't have the n here, we don't know where that 0 is of gn. Maybe that 0 is somehow close to z2. And that was the danger. We need to make sure we can keep gn away from 0 at the point z2. This integral is going to be 0. Okay? None of the gn's are 0 near z2. The only place where there's 0 is at z1. I just choose the radius here to be so small that z1 is outside. That's all I need. Question or? Okay.
Do we know about gn prime?
Since gn is holomorphic, gn prime exists,
Okay.
and then we can just apply the argument principle. So this is by the argument principle.
Wait, how is it by the argument principle?
Isn't that what it counts the number of zeros minus the number of poles?
Yeah.
They call that the argument principle.
Oh, okay. Sure.
And so there is nothing to count. It has no zeros, it has no poles. It's very important that gn doesn't vanish. And since gn is holomorphic, there's clearly no poles. So if this equals 0, what would happen if I take the limit as n goes to infinity? What would I get? 0. Right? This is the kindest limit I can give you. Right? What is the limit as n goes to infinity of 0? Right? It's 0. So if I wanted to, I could write the limit as n goes to infinity and put a 1 over 2 pi I over here. What would you like to do? Interchange, right? You want to wave your magic wand and move the limit inside the integral. And if you do that, you would then get 1 over 2 pi I, the integral of Gn, I'm sorry, of G of zeta prime over G of zeta d zeta. And let's assume for now that we can do that. What would this integral equal?
1/2.
We would divide it by 2 pi r. So
I'll go with 2 pi. -2.
-2. I think you might have said it.
1.
Equals 1. Why does it equal 1?
Because that has 1 0 inside.
Yeah.
G has 1 0 inside. G is 0 at Z2. G is also 0 at Z1. G may be 0 at many other places. But I've chosen a sufficiently small disk so that there are no more zeros of G other than Z2 inside that disk.
Isn't it a negative one? Isn't it zeros minus poles? Isn't there a pole in this?
No. It's a 0 of G. So this expression counts
yeah,
the number of zeros of G minus the number of poles of G. So this would just be equal to 1. So we just choose a small enough disk around Z2 so that no other zeros of G are close by. We know we can do that because if we didn't, then on every radius we'd have a 0, and then that would accumulate, and then G would be constant. If G is constant, F differs from G by subtracting a constant, so F would be constant. We assumed F is not constant. F takes on at least 2 values. So it just goes all the way backwards. So the only thing we have to justify is moving the limit inside the integral. Right? Because we are in this part of the Boltzmann science complex. We justify these things. How can we justify it?
Uniform convergence.
Yeah, uniform convergence, right? What's the one condition
Oh,
we
yeah.
really haven't used yet? So what do you think would be an interesting problem? Yeah, well, what would happen if you don't have uniform convergence? Well, because we have uniform convergence, I'm staying a fixed distance away from Z2 when I'm doing this integral. My function G is going to converge to something that's non-zero. Everything is fine, and I can interchange because of the uniform convergence. I can look at the difference between these two integrals and subtract and show that it's going to go to 0 because the denominators are bounded away from 0, and everything is fine. So this is okay by the uniform convergence. Okay. So there's a lot of really good ideas in this proof. There's the accumulation principle, there's the argument principle, there's using uniform convergence to justify doing an interchange. Okay. There's the difficulty of finding the right functions to look at. And again, we need to control what is going on. We want to understand where things are happening. I can define this without the n here, and it will still have only 1 0, but I don't know where that 0 is, and I don't want things to be hopping and moving over. Somehow, another 0 is magically appearing in the limit, and the difficulty is that should not be happening. We should not have a 0 being somehow created from the sequence of one-to-one functions.
Yeah, can we go one more time?
Yep.
Once we get that 1, that's a contradiction because
1 is non-zero.
not 0, right? Okay.
So that is a prerequisite for this class. I will assume you know that 1 is not equal to 0.
Yeah.
If you do not know the difference of that, you may have one more M&M.
Okay.
No, it's actually 0 more M&Ms.
No,
Because one
I
is
figured it
equal
out
to
in the
0.
middle.
Oh, you figured it out in the middle? Okay.
You said
Oh,
1.
okay. So this is, so again, it's what contradiction do you want to gun for? This is a really good contradiction. I'm counting how many zeros I have, and this way I get a count of 1, this way I get a count of 0 contradiction. Okay, so this was the final thing we needed because we wanted the function that we got in the Riemann mapping theorem in step 2, we wanted that to be a one-to-one function. And if it wasn't a one-to-one function, we would have a problem. So the whole point of all this was to allow us to say we have a one-to-one function. Okay. Any other questions on Riemann mapping before we call it done? Alright, so this officially finishes chapter 8. Alright, so we've covered all the core stuff that I want to cover in terms of the material for the class. The rest is now up to you guys with veto power by myself in terms of what we cover. Alright, there is no way I can teach a class in complex analysis and not do some number theory, especially the Riemann Zeta function. Alright, my advisor, I think, would justifiably shoot me for doing this.
Why?
So, the best answer to that is actually something I was going to say anyway. So
Oh.
I can be like a politician going to my prepared speech. Whenever you're studying a subject, it's very unnatural. You have this beautiful book, and everything is so logically presented in order. Oh, we have this lemma, this builds up to this theorem, and then we use the, it's all developed very nicely. It's nice to look at the history of the subject and try to understand how did people investigate, what did they choose to investigate, what was the motivation behind a lot of what they were doing. A lot of complex analysis was designed to study things in number theory. And as this is the source of motivation for a lot of the results, I think it's worth seeing its origins, seeing what problems inspired people. So we're not going to get into the full nuts and bolts of the proof of the prime number theorem. I will give you a physicist's proof of the prime number theorem, and leave some as calculations for you to do. And this will motivate a lot of what we're doing. A lot of stuff on the Riemann Zeta function was proved by the big guns in complex analysis that came later. How many of you have ever looked at, how many of you have heard of the Riemann hypothesis? Okay. One of the biggest open problems in all of mathematics. I got into trouble in my early years at Williams for having too many advanced, side remarks. If you look at Riemann's original paper, talk about a side remark, it's like this throwaway sentence. And wouldn't it be nice if the zeros were distributed as symmetrically as possible? But as it's not directly relevant to what I'm doing now, I'll leave that for the future. So I will make available, Riemann's original paper. It's very interesting to see how it's done. The other thing is at the very end of the Fourier packet handout, I included some of the most famous papers in the past few decades that have been rejected. My favorite was the one where the author was told to use English titles for English journals. But if you haven't read that, I strongly urge you to read these negative reviews and take heart whenever anybody objects to the work you're doing. These are some of the biggest pivotal papers, very computer sciencey heavy, if you notice that. One of them was basically saying RSA, this is useless. We only need like 12 computers in the world. Who's going to be sending email other than academics?
How much damage could be caused by a peer reviewer having a bad day?
Yes. The other one that I really liked was they should submit this paper to a journal that's not peer reviewed so that nobody will read it. So, if you go to the, I may get this wrong, how many of you have seen The Life of Brian? The Life of Brian. So this is like the Judean liberation, the People's Front of Judea and the Judean Liberation Front. They basically permute the names. I will get the names slightly wrong. This is the Interdisciplinary Journal of Mathematics. And a couple of years ago I was given a paper to write a review for Math372 for them, which had a published proof of the generalized Riemann hypothesis and a disproof of the Birch-Swinnerton die conjecture, all in the same article. It was building on the author's previous proof of the Riemann hypothesis. Now, the Riemann zeta function is normally defined as the sum n goes from 1 to infinity of 1 over n to the s, or sometimes you might write it as n to the negative s. The paper I had to write a review for Math372 defined it a little bit differently. He instead did n to the tilde s, because he was a logician and he used tilde for negation. So this gives you an idea of what the paper was like. So Math372, for those of you who are continuing to grad school, if you don't know what Math372 is, this is something you should become familiar with. If you want to write reviews for Math372, let me know. It's a chance to just get a quick executive summary of what the paper is, and then you can figure out, is it worth reading? You're not supposed to, for the most part, editorialize. So when I was given this paper to write a review for, I had to be very careful as to how I wrote the review.
Oh, that was a published paper?
It was a published paper in the Interdisciplinary Journal of Mathematics. And so the net result was I complained to Math372, and within 4 hours of my complaint, the journal was banned from Math372 for allowing this to get through.
Wow.
No, I mean, if you have any serious editorial, you're not going to have a proof of the Riemann hypothesis, and a proof of the generalized Riemann hypothesis, and a disproof of the Birch-Swinnerton die conjecture coming into a paper like this, coming into a journal like this. So here's the sum of 1 over n to the s. It turns out this sum has another formulation. And I can write it as a product p is prime of 1 minus 1 over p to the s inverse. So when you see something like this, what's the first thought that should go through your mind?
Does it make sense?
I'm sorry? Good, does it make sense? So for what values of S does this make sense? So it turns out everything is okay if the real part of S is greater than 1. Unfortunately, I'm going to have to use some results from multivariable calculus. I apologize. Might be Calc 1, depending on how you had it. They called it a P series, the sum of, n to the 1 over n to the P. The sum of 1 over n to the P converges if P is greater than 1, diverges if P is less than or equal to 1. It's absolutely horrible here because here we want P to be a prime, and we're using S. But as long as S has real part greater than 1, this converges. Now, the question Pat was asking was, who cares? A couple of years ago, I had a student presenting research he had done with me over the summer at a conference. This was the Young Mathematicians Conference. And he gave 3 reasons for why you care about these properties of the class number. I forget what the first 2 was, but his third one was because my advisor is funding me. And for a lot of things in life, that is a pretty good reason. The person who owns the lab, they want to study this. I'm the peon. They're the master. I will study this. If you care about primes, this is a really good thing to study. So I need a volunteer. I need 2 volunteers. Okay. All right, we're going to the back. I need the next integer after 2013.
2014.
Okay, I need the next prime after 2013.
2017.
So I know it's not 14 or 16. I know it's not 15. 17 is possible. As a rule of thumb, you should always have the next year prime known in advance for something like this. It's not going to be divisible by 7, so it's passing a lot of the tests. So
2017.
So close enough. We'll call that worth an M&M. Okay. Why wouldn't it be 2019? Divisible by 3, because the sum of the digits is a multiple of 3. The integers, there's really not that many mysteries left about the distribution of integers. Nothing, you're a great student and everything. It's not that hard to give the next integer after a given integer.
2017 is prime.
All right. That's worth 2 M&Ms. It's not worth 2017 M&Ms. Okay? There's no mysteries in the location of the integers. So the hope is, if I can understand the integers, I can use this link to deduce information about the primes. Does this expression here look like anything you've seen before?
Hadamard's product.
Not Hadamard.
Yeah, the golden.
Nope. So much of life is how you write the algebra. I'll write the algebra in a little bit more illuminating manner. The product over P, 1 over 1 minus 1 over P.
It's a geometric series.
It's a geometric series.
Oh my.
So when you write it like this, now it's clear, but when you write it like this, you guys have trouble.
Yeah.
So when you So it's here, a lot of life is pattern recognition. Okay? So if you expand this series out, and you play convergence games, you can actually show that this product is the same as this sum, and the sum is the same as this product. So what you would do is you would take the sum and you would truncate it some far way down, you would take the product, truncate it some far way down, and then show that the difference tends to 0 as the truncations go to infinity. And as long as the real part of S is greater than 1, things converge. And so I'm not going to go through the proof, but I will say you need to use a fundamental theorem to prove that these two are the same. Does anybody know what the key ingredient we need? You don't know that many fundamental theorems.
Algebra.
Fundamental theorem of algebra says every polynomial of degree n has n roots.
Calculus.
I'm sorry?
Calculus.
Just go and have a list.
No, can't be calculus.
Fundamental theorem of complex.
Fundamental theorem of arithmetic. It's not the fundamental theorem of linear algebra because I do not accept it as a fundamental theorem. It's not going to be algebra because I haven't even taken a class in algebra. No, it's not algebra because we don't have a polynomial that was setting equal to 0. It's fundamental theorem of arithmetic.
There's a fundamental theorem. Okay.
And so the fundamental theorem of arithmetic says the following. You can write any number n uniquely as a product of prime powers. Yes.
Oh.
And P1 less than P2 if I write them like this, the product is unique.
I see.
Because otherwise, you know, I don't really care about reordering the factors. That's not a big deal. So if you have the primes in increasing order, you give me an integer. There is one and only one way to write it as a product of prime powers. So some of you have tested Cam on his knowledge of primes, and you know, it's pretty good.
That's pretty good.
And
Yeah,
Cam
up to the
knows.
50s, I think.
Yeah, and Cam knows what the smallest prime is. What's the smallest prime?
2.
What's the definition of prime?
Divisible by itself in 1.
But we don't let 1 be a prime.
So wait, if the definition of prime is you're only divisible by yourself in 1,
No,
What
the
are we-
Math Advisory Board decided that 1 was not a prime. So
are you on
it's not a
SMASAP?
prime. Yeah.
Okay, you can say SMASAP has. No, there are legislatures
No, no.
in America that declared pi equals 3 or pi equals 4.
They don't have the authority.
They don't have the same authority as SMASAP.
The secret council of mathematicians, existing somewhere off in France, decided this.
The problem is the French mathematicians don't actually exist. This is true. This
They're
is true.
theoretical.
No, look up the mathematician Bourbaki. He's written at least 20 books, and Bourbaki does not exist. So look up Bourbaki.
Is it a pen name?
Yeah, he's spell right. THAT.
How do you spell?
Okay.
Oh, Boulder.
So look up Bourbaki. Okay. And then you'll see, well, things are being recorded, so I will stop there. I'll say anything else, but I don't want to insult the whole country. You know, I'm too busy to conquer them this week. Okay, so what number is being left off the list of primes? 1 is not being listed as a prime. If the definition of prime is you're only divisible by 1 in yourself, shouldn't 1 be on the list?
But then there are infinite number of prime factorizations.
That's right. And so the reason we have made the executive decision not to declare 1 prime is we want the fundamental theorem of arithmetic to hold. We want every number to have a unique factorization as a product of prime powers. If 1 were prime, I could put in as many factors of 1 as I want. So we have made the executive decision that 1 is not prime. So 1 actually has a special name.
Pseudo prime?
I'm sorry?
Social prime.
Nope.
Unit.
Unit. So we call 1 a unit. And so the 2 units for the integers are 1 and -1. If you do number fields, you can have other units as well. And so in fact, you know, numbers of the form e to the I theta, if theta is, you know, a certain rational multiple of 2 pi, those will be units in a lot of these cases. So we don't want 1 to be a prime because we want the fundamental theorem of arithmetic. As a really nice exercise, I encourage you to prove these two are the same by expanding the geometric series formula. And since every number can be written uniquely as a product of primes, when I expand these different factors, if I want the number, you know, 1 over 2 cubed, 3 to the 5th, you know, 7 squared, oh, well, that tells me exactly which 2 I want, which 3 I want, which 7 I want, and then I take 1 for every other term in the product. Okay, so now what I want to do is I want to look at some of the consequences of just the existence of the zeta function. So zeta of s is the sum, n goes from 1 to infinity, 1 over n to the s. It's the product over primes of 1 minus p to the minus s inverse, at least if the real part of s is greater than 1. What value of s should I evaluate this at?
0.
Why do you put 0?
Didn't get 1 over 0.
Greater than 1.
Yeah.
Yes.
We can't evaluate it at 0. 2 is a good choice. So who knows what the sum of 1 over n squared is?
It's a pi.
There is a pi in it.
Oh yeah, it's a 6.
Oh,
It has
it's
pi over
pi
6.
squared over 6.
Pi squared over 6.
Yeah.
Wasn't that a colloquial?
That was a colloquial.
Yeah.
I mean, this is hit at least every 2 years, if not more frequently, for colloquial.
Really?
Yeah, it's a very famous one.
We
will-
will.
We'll give a proof of this when we turn to Fourier series. We'll prove that the sum of 1 over n squared is pi squared over 6. Here's the interesting fact. This proves that there are infinitely many primes if you know just a little bit about pi squared. What kind of number is pi squared?
Irrational.
Okay, it's irrational. What else? Transcendent. I actually don't need the full strength of transcendence. I just need to know that pi squared is irrational. So I will assume two assumptions. I'll assume we know that it's pi squared over 6, and I'll assume we know that it's not rational. If you haven't seen this before, how does this imply that there are infinitely many primes? Excellent. If there are only finitely many primes, this product is finite and rational. So, if only finitely many primes, it implies zeta of 2 is rational. Contradiction. Now what's interesting is this gives us no understanding of how quickly the number of primes grow. So we define pi of x to be the number of primes p less than or equal to x. As primes are the building blocks of numbers, by the fundamental theorem of arithmetic, I want to know how many building blocks do I have up to a given level. So this is the most important function to study, is how many primes are there up to x. And we will see later in this course the prime number theorem tells us it's about x over log x. And we'll see a sketch of a proof of that. What's sad about this statement is it doesn't give us any information about how many primes there are up to x. It just says if there's not infinitely many, bad happens. And so in order for bad not to happen, the only way that can, we must have infinitely many primes. So I actually have, I'll try over here, this is the prime number theorem. It tells us it's about x over log x. I have a paper that I'm working on, if anybody wants to join in, that's great, where by knowing how irrational pi squared is, you can actually use that to quantify how many primes there are. The original proof I had subtly assumed the prime number theorem, because that was how we actually understood how irrational pi squared was. And I was able to then prove that there's something like log x primes up to x by knowing that there's x over log x primes up to x. So not a good result. And so I've been working to try to see exactly how far can you push things. And so amazingly, you can get really close to x over log x, you can get very close to the prime number theorem from looking at how irrational pi squared is. It's a very geometric argument. If anybody's interested, let me know. I'm happy to talk to you about stuff like that. So this is called a special value proof, because we're looking at the zeta function at a special value. Okay, can anybody think of another value of s to look at? So you could look at 4, so all the even integers, it turns out, give you a multiple of pi to that power, a rational multiple of pi to that power. We don't know about the odds.
Don't we know that for 3 it's...
We know zeta of 3 is irrational, we don't know if it's transcendental. And we have results such as, if you look at like zeta 3, zeta 5, zeta 7, zeta 9, at least so many of these are irrational. We have some strange results like that. There is another value of s that's worth looking at. Not as it approaches infinity. As s goes to infinity, what do we get? We just get 1. So go the other way. Don't go to infinity. What should you go to?
Go to 1.
Yeah, go to 1. So the limit, as s goes to 1, I'm going to write a plus sign. The plus sign means I'm approaching it from above. What does that go to? So what happens as s goes to 1? So I have the sum of 1 over n to the s with s getting closer and closer to 1. So it's approaching the harmonic series. So this goes to infinity. So what can you deduce about the number of primes? There must be infinite many.
Deduce that twice.
So what I'm going to do now, was there a question? What I'm going to do now is I'm going to give you a quick estimate of how to go from, this is the harmonic series and it diverges, to an estimate of how many primes there are. I'm not going to worry about doing everything carefully and rigorous.
What do you mean by an estimation of how many? You're talking about estimation of how many primes will blow a bound, right?
I want to understand how quickly does the function pi of x grow? How many primes are there up to x? And I can actually get some estimates for this by knowing how the harmonic series diverges. So what I want to do a little bit for the last part of the semester is some things I will prove rigorously, like the uncertainty principle in quantum mechanics, but other things I want to just give you some sense of what's going on and not put in all the details. If you're going to become a number theorist, then you want to put in all the details. But if not, you want to just get a sense. So I'm going to define zeta sub x of s to be the sum n less than or equal to x of 1 over n to the s. And what do you think this is approximately equal to? Approximately, which part of the
Product of primes less than 1.
Yeah, I mean, I've got to be a little bit careful. It should be, similar to the product of primes less than or equal to x. Clearly, everything here is going to be contained in here. But this will have a few other terms as well. But they'll all be terms beyond x. So let's just say roughly they're the same. So if I take s equals 1, zeta x of 1 is the sum 1 over n less than or equal to x, and this is approximately the product p less than or equal to x, 1 minus 1 over p, rest. What's the sum of 1 over n up to x? This is approximately?
X minus 1.
I'm sorry?
Log x.
But it's about log x, right? The sum of the harmonic numbers up to x is about log x. Now I want to understand this. So what I'm going to do is I'm going to take the exponential of the log of the product p less than or equal to x, 1 minus 1 over p in this. Whenever we see a product, we always want to take logs. And if I just exponentiate, I get back to where I started. So now we get the log of x is approximately the exponential of negative sum p less than or equal to x, the log of 1 minus 1 over p. Approximately, what's the log of 1 minus 1 over p?
1 over p.
I'm sorry?
1 over p.
Almost.
Plus 1 over p.
Oh,
Squared.
nope.
Minus 1 over p.
No.
You just think of the terms.
The log of 1 minus 1 over p. It's not approximately 1 over p. You're close.
Is 1 over p?
No. Negative 1 over p. I've got a minus sign. Right? This is a number a little bit less than 1. So its logarithm should be less than 0. So we get the log of x is approximately the exponential of negative the sum p less than or equal to x of 1 over p. If I take the log of both sides, the exponential vanishes. Oh wait, I'm sorry, the negative and the negative reinforce. So if I take the log of both sides, I get the sum p less than or equal to x of 1 over p is approximately log x. The sum diverges. Okay? The sum of the reciprocals of the primes diverges. And again, you can make all of this rigorous and accurate. This is not rigorous and accurate. You can clean this up. So the first thing is, do you buy it? Does this seem reasonable that the sum of 1 over p is like log x?
It doesn't make sense to me intuitively, but
Well, do you know anything that looks like 1 over p? Any other sequences?
1 over n.
1 over n. So if you sum the reciprocals of the integers, you get log x. There's a lot fewer primes than integers, so it should be smaller than log x. So log x is at least reasonable. What you want to then try to do is what's called partial summation. If I know the sum of the reciprocals, can I deduce something about just the sum of 1? And so if you've seen partial summation, I can write 1 over p times p as 1. And I can try to do basically summation by parts, or partial summation or integration by parts, and use the knowledge of this sum to get knowledge of the sum of 1, which would count how many primes there are. So in some sense, the zeta 1 proof beats the hell out of the zeta 2 proof. Zeta of 2 just told us there's infinitely many primes. This tells us there's so many primes that the sum of their reciprocals diverges. Can you give me an infinite sequence whose sum of reciprocals does not diverge? I'm sorry?
1 over n squared.
Yeah, the integer squares. The sum of the reciprocals of the squares converges. In fact, we saw in Zeta of 2, it converges to pi squared over 6. What this tells you is there are far more primes than perfect squares. Okay? So in some sense, we've at least gotten that answer out of what we've done today. And so there's a lot more we can say on this. So what I was going to do is I'm going to continue and do a little bit more about the zeta function on Wednesday. I'm going to talk a little bit about the analytic continuation of the zeta function, and I'll motivate this in terms of analytic continuations of other things in complex analysis we've seen. And then we're going to reach a stumbling block. And then once we reach that stumbling block, we will be sufficiently motivated to do Fourier analysis, which will lead into the quantum mechanics. But this way, for the people who don't care about quantum mechanics, here's at least a motivation for why we will do the quantum mechanics.